Hello everyone, I am Arti from BSc Chemistry Honors second year. Today I am going to read out the chapter States of Matter. Chemical properties of a substance don't change with the change of its physical state, but rate of chemical reaction do depend upon the physical state. Many times in calculation while dealing with the data of experiment we require knowledge of the state of matter. Therefore it becomes necessary for a chemist to know the physical laws which govern the behavior of matter in different states. In this unit we will learn more about these three physical states of matter, particularly liquid and gaseous state. To begin with, it is necessary to understand the nature of intermolecular forces, molecular interaction and effect of thermal energy on the motion of particle, because a balance between these determines the state of a substance. Intermolecular forces. The intermolecular forces are the force of attraction and repulsion between interacting particles, atom and molecules. These terms don't include the electrostatic forces that exist between the two oppositely charged ion and the force that hold atom of a molecule together, covalent bonds. Attractive intermolecular forces are known as van der Waals forces in honor of Dutch scientist Johannes van der Waals, who explained the deviation of real gases from the ideal behavior through these forces. We will learn about this later in the unit. Van der Waals forces vary considerably in magnitude and include dispersion forces or London forces, dipole forces and dipole induced dipole forces. A particularly strong type of dipole interaction is hydrogen bonding. Only a few elements can participate in hydrogen bond formation, therefore it is treated as a separate category. At this point it is important to note that attractive forces between an ion and a dipole are known as ion dipole forces, and these are not van der Waals forces. We will now learn about different type of van der Waals forces: dispersal forces or London forces. Atom and non-molecular molecules are electrically symmetrically and have no dipole moment because their electronic charge cloud is symmetrically distributed, but a dipole may develop momentarily even in such atoms and molecules. This can be understood as follows. Suppose we have two atoms A and B in the close vicinity of each other. It may so happen that momentarily electronic charge distribution is one of the atoms, say A, become unsymmetrical. That is, the charge cloud is more on one side than the other. This results in the development of instantaneous dipole on the atom A for a very short time. The instantaneous or transient dipole distorts the electron density of the other atom B, which is close to it, and as a consequence a dipole is induced in the atom B. The temporary dipole of atom A and B attract each other. Similarly, temporary dipole are induced in molecule also. This force of attraction was first proposed by the German physicist Fritz London, and for this reason the force of attraction between two temporary dipole forces activate when the molecules possessing permanent dipole ends of the dipole possess partial charge, and those charges are shown by Greek letter delta. Partial charges are always less than the unit electronic charge. The polar molecule interact with neighboring molecule, shows electron cloud distribution in the dipole of hydrogen chloride, shows dipole interaction between two HCl molecules. This interaction is stronger than the London force because it is weaker than ion-ion interaction because only particle charges are involved. The attractive force decreases with increase of the distance between the dipoles. As in the above case, here also the interaction energy is inversely proportional to the distance between polar molecule. Dipole-dipole interaction energy between stationary polar molecule is proportional to 1 by r cube, and that between rotating polar molecule is proportional to 1 by r की power 6, where r is distance between polar molecule. Beside dipole-dipole interaction, polar molecule can interact by London force also. Thus, cumulative effect is that the total of the intermolecular force is in polar molecule increase. Dipole-induced dipole force. This type of attractive force operates between the polar molecules having permanent dipole and the molecule lacking permanent dipole. Permanent dipole of the polar molecule induced dipole on the electrically neutral molecule by deforming its electronic cloud. Thus, an induced dipole is developed in other molecule. In this case also, interaction energy is proportional to 1 by r की power 6, where r is the distance between two molecules. Induced dipole moment depend upon the dipole moment present in permanent dipole and polarizability of the electrically neutral molecule. We have already learnt in unit 4 that molecule of larger size can be easily polarized. High polarizability increase the strength of attractive interaction. Hydrogen bond. As already mentioned in session 5.1, this is special case of dipole-dipole interaction. We have already learnt about this in unit 4. This is found in the molecule in which highly polar NH, OH and HF bonds are present. Although hydrogen bonding is regarded as being limited to nitrogen, oxygen and fluorine, but species such as chlorine may also participate in hydrogen bonding. Energy of hydrogen bond varies between 10 to 100 kg per mole. This is quite a significant amount of energy. Therefore, hydrogen bonds are powerful force in determining the structure and properties of many compounds. For example, protein and nuclei acids. Strength of the hydrogen bond is determined by the Coulombic interaction between the lone pair electrons of the electronegative atom of one molecule and the hydrogen atom of other molecule. Following diagram shows that formation of hydrogen bond HF. Intermolecular forces discussed so far are all attractive. Molecules also exert repulsive force on one another. When two molecules are brought into close contact with each other, the repulsion between the electron cloud and that between the nuclei of two molecules come into play. Magnitude of the repulsion rise very rapidly as the distance separating the molecule decrease. This is the reason that liquid and solid are hard to compress. In this state, molecules are already in close to contact, therefore they resist further compression, as that would result in the increase of repulsive attraction. Thermal energy. Thermal energy is the energy of a body rising from motion of its atom or molecule. It is directly proportional to the temperature of the substance. It is the measure of average kinetic energy of the particle of matter and is thus responsible for movement of particle. This movement of particle are called thermal motion. Intermolecular forces versus thermal interaction. We have already learnt that intermolecular forces tend to keep the molecule together, but thermal energy of the molecule always to keep them apart. Three states of matter are the result of balance between intermolecular forces and the thermal energy of the molecule. When molecular interaction are very weak, molecules don't cling together to make liquid or solid unless thermal energy is reduced by lowering the temperature. Gas don't liquefy one compression only, although molecules come very close to each other and intermolecular forces operate to the maximum. However, when thermal energy of the molecule is reduced by lowering the temperature, the gas can be very easily liquefied. Predominance of thermal energy and the molecular interaction energy of a substance in three states is depicted as follows. We have already learned the cause for the existence of the three states of matter. Now we will learn more about the gaseous and liquid state and the laws which govern the behavior of matter in this state. We shall deal with the solid state in class 12th. The gaseous state. This is the simplest state of matter. Throughout our life, we remain immersed in the ocean of air, which is mixture of gases. We spend our life in the lowermost layer of the atmosphere called troposphere, which is held to the surface of the earth by gravitational force. The thin layer of atmosphere is vital to our life. It shields us from harmful radiation and contains substances like dioxygen, dinitrogen, carbon dioxide, water vapor, etc. Let us now focus our attention on the behavior of substance which exist in the gaseous state under normal condition of temperature and pressure. A look at the periodic table show that only 11 elements exist as gases under normal condition. The gaseous state is characterized by the following physical properties. Gas are highly compressible. Gas exert pressure equally in all directions. Gases have much lower density than the solid and liquids. The volume and the shape of gases are not fixed. These assume volume and shape of the container. Gas mix evenly and completely in all proportion without any mechanical add. Simplicity of the gas is due to the fact that the force of interaction between their molecules are negligible. This behavior is governed by some general laws which were discovered as a result of their experimental studies. These laws are relationships between measurable properties of gases. Some of these properties like pressure, volume, temperature and mass are very important because relationship between these variables describe state of gas. Interdependence of these variables leads to the formulation of gas law. In next session we will learn about gas law. The gas laws which we will study now are the result of research carried on for several centuries on the physical property of gases. The first reliable measurement on property of gas was made by Anglo-Irish scientist Robert Boyle in 1662. The law which the formulated is known as Boyle's law. Later on, attempts to fly in air with the help of hot air balloons motivated uh, and Joseph Lewis Gay Lussac to discover additional gas laws. Contribution from Avogadro and others provided lot of information about gaseous state. Boyle's law, pressure volume relationship. On the basis of his experiment, Robert Boyle reached to the conclusion that on constant temperature, the pressure of fixed amount, that is number of moles n of gas, varies inversely with its volume. This is known as Boyle's law. Mathematically it can be written as P is directly proportional to 1 by V. Here V represent volume. P equal to K into 1 by V, where K is proportionality constant. The value of constant depend upon the amount of gas, temperature of the gas and the unit in which P and V are expressed. On rearranging equation, we obtain PV equal to K. It means that at constant temperature, product of pressure and volume of a fixed amount of gas is constant. If a fixed amount of gas at constant temperature T occupying volume V1 at pressure P1 undergoes expansion, so that volume becomes V2 and pressure become P2, then according to Boyle's law, P1 V1 equal to P2 V2 equal to constant. P1 pressure 1 upon P2 equal to V2 by V1. Figure 5.5 shows two conventional ways of graphically presenting Boyle's law. The value of K1 for each curve is different because for a given mass of gas, it varies only with temperature. Each curve corresponds to a different constant temperature and is known as an isotherm. Higher curves correspond to higher temperature. It should be noted that volume of the gas double if pressure is halved. Uh, Effect of pressure on volume of 0.0 mole of CO2 at 300 K. It is a straight line passing through the origin. However, at high pressure, gases deviate from Boyle's law, and under such condition, a straight line is not obtained in the graph. Experiment of Boyle's in a quantitative manner prove that gases are highly compressible because when a given mass of gas is compressed, the same number of molecules occupy a smaller space. This means that gases become denser at high pressure. A relationship can be obtained between density and pressure of a gas by using Boyle's law. By definition, density D is related to mass m and volume V by the relation D equal to m by V. If we put the value of V in this equation from Boyle's law equation, we obtain the relationship T equal to m by K1 into P equal to K dash P. This shows that at constant temperature, pressure is directly proportional to the density of the fixed mass of the gas. Charles' law, temperature volume relationship. Charles and Gay-Lussac performed several experiments on gases independently to improve upon hot air balloon technology. Their investigation shows that for a fixed mass of gas at constant pressure, volume of gas increases on increasing temperature and decreases on cooling. They found that for each degree rise in temperature, volume of gas increased by 1 by 273.15 of the original volume of gas at 0 degrees Celsius. Thus, if volume of the gas at 0 degrees Celsius and at T Celsius are V naught and Vt respectively, then Vt equal to V naught plus by 2 equal to Vt equal to V0. At this stage, we define a new scale of the temperature such that Tc on new scale is given by T equal to 2.73.15 plus T and 0 degree Celsius will be given by T0. This new temperature scale is called Kelvin temperature scale or absolute temperature scale. Thus, 0 degree Celsius on the Celsius scale is equal to 273.15 Kelvin at absolute scale. Note the degree sign is not used while writing the temperature in absolute temperature scale. Kelvin scale of temperature is also called thermodynamic scale of temperature and is used in all scientific work. Gay-Lussac law, pressure temperature relationship. Pressure in well inflated tires of automobiles is almost constant, but on a hot summer day this increases considerably and tire may burst if pressure is not adjusted properly. During winters, on a cold morning, one may find the pressure in the tires of the vehicle decreased considerably. The mathematical relationship between pressure and temperature was given by Joseph Gay-Lussac and is known as Gay-Lussac law. It states that at constant volume, pressure of a fixed amount of a gas varies directly with the temperature. Mathematically, P inverse directly proportional to temperature, P by T equal to constant. This relationship can be derived from Boyle's law and Charles' law. Pressure versus temperature graph at constant molar volume is shown in figure 5.7. Each line of this graph is called isochord. Avogadro law, volume amount relationship. In 1811, Italian scientist Amedeo Avogadro tried to combine conclusion of Dalton's atomic theory and Gay-Lussac law of combining volumes, which is now known as Avogadro law. It states that equal volume of all gases under the same condition of temperature and pressure contain equal number of molecules. This means that as long as temperature and pressure remain constant, the volume depend upon the number of molecules of the gas, or in other words, amount of the gas. Mathematically, we can write direct V volume directly proportional to n. N is the number of the mole of the gas. V equal to K for n. The number of the molecule in 1 mole of a gas has been determined by 6.02 into 10 raised to power 23 and is known as Avogadro constant. You will find that this is same number which came across while discussing definition. Since volume of gas is directly proportional to the number of moles, 1 mole of each gas at standard temperature and pressure will have same volume. Standard temperature and pressure means 273.15 Kelvin at 0 degrees Celsius temperature and 1 bar exactly 10 raised to power 5 Pascal pressure. These values approximate freezing temperature of water and atmospheric pressure at sea level. At STP, molar volume of an ideal gas or a combination of ideal gas is 22.71098 liter per mole. Molar amount of same gas is given in table 5.2. Number of mole of gas can be calculated as follows. Number of moles equal to m by m, where small m represent mass of the gas under investigation and capital M represent molar mass. V equal to K for m by m. A gas that follows Boyle's law, Charles' law, and Avogadro's law strictly is called an ideal gas. Such a gas is hypothetical. It is assumed that intermolecular forces are not present between the molecule of an ideal gas. Real gases follows this law only under certain specific conditions, when forces of interaction are particularly negligible. In all other situations, these deviate from ideal behavior. You will learn about the deviation later in this unit. Ideal gas equation in three laws which we have learnt till now can be combined together in a single equation, which is known as ideal gas equation. At constant temperature and number of moles, volume inversely proportional to pressure. At constant P and N, volume is directly proportional to temperature. At constant P and T, volume is directly proportional to number of moles. So V is directly proportional to N into T by P. V equal to R and Tp by P, where R is proportional constant. On rearranging the equation, we obtain PV equal to nRT, R equal to PV by NT. R is called real gas R is called gas constant. It is same for all gases, therefore it is called universal gas constant. Dalton's law of partial pressure. The law was formulated by John Dalton in 1801. It states that the total pressure exerted by the mixture of non-reactive gases is equal to the sum of the partial pressure of individual gases. The pressure which these gases would exert if they were enclosed separately in the same volume and under the same condition of temperature. In a mixture of gases, the pressure exerted by the individual gas is called partial pressure. Mathematically, P total equal to P1 plus P2 plus P3, where P total is the total pressure exerted by the mixture of gas and P1, P2, P3, etc. are partial pressure of gases. Gases are generally collected over water and therefore are moist. Pressure of dry gas can be calculated by subtracting vapor pressure of water from the total pressure of the moist gas which contain water vapor. Also, pressure exerted by saturated water vapor is called aqueous tension. Aqueous tension of the water at a different temperature is given in table 5.3. P dry gas equal to P total minus aqueous tension. Kinetic molecular theory of gases. So far we have learnt the laws, which are concise statement of experimental facts observed in laboratory by the scientist. Conducting careful experiment is an important aspect of scientific method, and it tells us how the particular system is behaving under different conditions. However, once the experimental facts are established, a scientist is curious to know why the system is behaving in that way. For example, gas law help us to predict that pressure increase when we compress gases, but we would like to know that what happen at molecular level when a gas is compressed. A theory is constructed to answer such question. A theory is a model that enable us to better understand our observation. The theory that attempts to elucidates the behavior of gases is known as kinetic molecular theory. Assumptions or postulates of the kinetic molecular theory of gases are given below. These postulates are related to atoms and molecules which can't be seen. Hence, it is said to provide a macroscopic model of gases. Gases consist of a large number of identical particles that are so small and so far apart on the average that the actual amount of the molecule is negligible in comparison to the empty space between them. They are considered as point masses. This assumption explains the great compressibility of gas. There is no force of attraction between the particles of gas at ordinary temperature and pressure. The support for this assumption comes from the fact that gases expand and occupy all the space available to them. Particles of gas are always in constant and random motion. If the particle were at rest and occupied fixed position, then a gas would have a fixed shape which is not observed. Particles of gas move in all possible directions in straight line. During their random motion, they collide with each other and with the walls of the container. Pressure is exerted by the gas. As a result, the collision of particle which with the wall of container. Collision of gas molecule are perfectly elastic. This means that total energy of molecules before and after the collision remains same. There may be exchange of energy between colliding molecules. Their individual energy may change, but the sum of their energy remain constant. If there were loss of kinetic energy, the motion of the molecule will stop and gases will settle down. This is contrary to what is actually observed. At any particular time, different particles in the gas have different speed and hence different kinetic energy. This assumption is reasonable because as the particle collides, we expect their speed to change. Even if initial speed of all particles was same, the molecular collision will disrupt this uniformity. Consequently, the particle must have different speed which go on changing constantly. It is possible to show that though the individual speeds are changing, the distribution of speed remains constant at a particular temperature. If a molecule have variable speed, then it must have a variable kinetic energy. Thus, these circumstances we can talk only about average kinetic energy. In kinetic theory, it is assumed that average kinetic energy of the gas molecule is directly proportional to the absolute temperature. It is seen that on heating a gas at constant volume, the pressure increases. On heating the gas, kinetic energy of particles increase and those strike the wall of the container more frequently, thus exerting more pressure. Kinetic theory of gases allows us to derive theoretically all the gas laws studied in the previous session. Calculation and predictions based on kinetic theory of gases agree well with the experimental observation and thus establish the correctness to this. Liquefaction of gases. First complete data on pressure, volume, temperature relation of a substance in both gaseous and liquid state was obtained by Thomas Andrews on carbon dioxide. He plotted isotherm of carbon dioxide at various temperatures. Later on, it was found that real gases behave in the same manner as carbon dioxide. Andrew noticed that at high temperature, isotherm look like that of an ideal gas and the gas can't be liquefied even at a very high pressure. As the temperature is lowered, shape of the curve changes and data shows considerable deviation from ideal behavior. At 30.98 degrees Celsius, carbon dioxide remains gas up to 73 atmospheric pressure. At 73 atmospheric pressure, liquid carbon dioxide appears for the first time. The temperature 30.98 Celsius is called critical temperature of carbon dioxide. This is the highest temperature at which liquid carbon dioxide is observed. Above this temperature, it is gas. Volume of 1 mole of the gas at critical temperature is called critical volume, and the pressure at this temperature is called critical pressure. Critical temperature, pressure, and volume are called critical constant. Critical temperature of a gas is the highest temperature at which liquefaction of the gas first occurs. Liquefaction is so-called permanent gases. Gases which show continuous positive deviation in Z value require cooling as well as considerably compression. Compression brings the molecule in close vicinity and cooling slows down the movement of molecules. Therefore, intermolecular interaction may hold the closely and slowly moving molecules together and the gas liquefy. It is possible to change a gas into liquid or liquid into gas by a process in which always a single phase is represented. Thus, there is continuity between the gaseous and liquid state. The term fluid is used for either a liquid or a gas to recognize this continuity. Thus, a liquid can be viewed as a very dense gas. Liquid and gas can be distinguished only when the fluid is below its critical temperature and its pressure and the volume lie under the dome. Since in that situation, liquid and gas are in equilibrium and a surface separating the two phases is visible. In the absence of this surface, there is no fundamental way of distinguishing between two states. At critical temperature, liquid passes into gaseous state imperceptibly and continuously. The surface separating two phases disappears. Liquid state. Intermolecular forces are stronger in liquid state than in gaseous state. Molecule in liquid are so close that there is a very little empty space between them, and under normal condition liquid are denser than gases. Molecule of liquids are held together by attractive intermolecular forces. Liquid have definite volume because molecules don't separate from each other. However, molecules of liquid can move past one another freely. Therefore, liquid can be powered and assume the shape of the container in which they are stored. In the following session, we will look into the some of the physical property of the liquid, such as vapor pressure, surface tension, and viscosity. Vapor pressure. If an evacuated container is partially filled with the liquid, a portion of liquid evaporates to fill the remaining volume of the container with vapor. Initially, the liquid evaporates and pressure exerted by vapor on the wall of the container. After some time, it becomes constant and equilibrium is established between liquid phase and vapor phase. Vapor phase at this stage is known as equilibrium vapor pressure or saturated vapor pressure. Since process of vaporization is temperature dependent, the temperature must be mentioned while reporting the vapor pressure of liquid. When a liquid is heated in an open vessel, the liquid vaporizes from the surface at the temperature at which vapor pressure of the liquid become equal to the external pressure. Vaporization can occur throughout the bulk of the liquid and vapor expand freely into the surrounding. The condition of free vaporization throughout the liquid is called boiling. The temperature at which vapor pressure of liquid is equal to the external pressure is called boiling temperature. At that pressure, vapor pressure of some common liquid at various temperature is given. At 1 atm pressure, boiling temperature is called normal boiling point. If pressure is 1 bar, then the boiling point is called standard boiling point of the liquid. Standard boiling point of the liquid is slightly lower than the normal boiling point because 1 bar pressure is slightly less than 1 atm pressure. At high altitude, atmospheric pressure is low. Therefore, liquid at high altitude boil at low temperature in comparison to that at sea level. Since water boil at low temperature on hills, the pressure cooker is used for cooking food. In hospitals, surgical instruments are sterilized in autoclaves while boiling point of water increased by increasing by the pressure above the atmospheric pressure by using a weight covering the vent. Boiling does not occur when liquid is heated in closed vessel. On heating continuously, vapor pressure increase. At first, a clear boundary is visible between liquid and vapor phase because liquid is more dense than vapor. At the temperature increase, more and more molecules go to vapor phase and density of vapor rises. At the same time, liquid becomes less dense. It expands because molecules move apart. When density of liquid and vapor become the same, the clear boundary between liquid and vapor disappears. This temperature is called critical temperature. Surface tension. It will known fact that liquid assume the shape of the container. Why it is then small drops of the mercury from spherical bead instead of separating on the surface. Why do particles of the soil at the bottom of river remain separated but they stick together when taken out? Why does a liquid rise in a thin capillary as soon as capillary touches the surface of liquid? All these phenomena are caused due to the characteristic property of liquid called surface tension. A molecule in the bulk of liquid experience equal intermolecular forces from all sides The molecule therefore does not experience any net force, but for the molecule on the surface of liquid, net attractive force in towards the interior of liquid due to molecule below it. Since there are no molecule above it, liquid tend to minimize their surface area. The molecule on surface experience a net downward force and have more energy than the molecule in a bulk, which don't experience any net force. Therefore, liquid tend to have minimum number of molecules at their surface. If surface of the liquid is increased by pulling a molecule from the bulk, attractive forces will have to be overcome. This will require expenditure of energy. The energy required to increase the surface area of the liquid by 1 unit is defined as surface energy. Its dimensions are uh, J meter per square. Surface tension is defined as the force acting per unit length perpendicular to the line drawn on the surface of liquid. It is denoted by Greek letter. It has dimension of kilogram per surface square, and in SI unit is expressed as the Newton per meter. The lowest energy state of the liquid will be when energy area is minimum. Spherical shape satisfy this condition. That is why mercury drops are spherical in shape. This is the reason that sharp glass edges are heated for making them smooth. On heating, the glass melt and the surface of the liquid tend to take the rounded shape at the edges, which make the edges smooth. This is called fire polishing of glass. Liquid tend to rise in the capillary because of surface tension. Liquid wet the things because they separate across their surface as thin film. Moist soil grains are pulled together because surface area of thin film of water is reduced. It is surface tension which gives stretching property to the surface of a liquid. On flat surface, droplets are slightly flattened by the effect of gravity, but in the gravity-free environment, drops are perfectly spherical. The magnitude of the surface tension of liquid depend on the attractive forces between the molecule. When the attractive forces are large, the surface tension is large. Increase in temperature increase the kinetic energy of the molecule, and effectiveness of the intermolecular attraction decrease, so surface tension decreases as the temperature is raised. Viscosity. It is one of the characteristic property of liquids. Viscosity is the measure of resistance to flow which arises due to the internal friction between layer of fluid as they slip past one another while liquid flows. Strong intermolecular forces between molecules hold them together and resist movement of layers past one another. When a liquid flows over a fixed surface, the layer of molecule in the immediate contact of surface is stationary. The velocity of the upper layer increases as the distance of layer from the fixed layer increases. This type of flow in which there is a regular gradation of velocity in passing from one layer to the next is called laminar flow. If we choose any layer in the following liquid, the layer above it accelerates its flow and the layer below it retards its flow. If the velocity of the layer at the distance dz is changed by the value du, then velocity gradient is given by the amount du by dz. A force is required to maintain the flow of layer. This force is proportional to the area of contact of layer and velocity gradient. F directly proportional to the area, and F directly proportional du by dz, where du by dz is velocity gradient, the change in the velocity with distance. F directly proportional into area into du by dz, here du by dz is velocity gradient. F equal to proportionality constant into a du by dz. N is proportionality constant and is called coefficient of viscosity. Viscosity coefficient is the force when velocity gradient is unity and the area of contact is unit area. Thus, coefficient of viscosity is measure of viscosity. SI unit of viscosity coefficient is 1 Newton second per square meter equal to Pascal second. Pascal second equal to 1 kilogram per meter per second. In CGS system, the unit of coefficient of viscosity is poise, named after great scientist Jean Louis Poiseuille. 1 poise equal to 1 gram per centimeter per second. Greater the viscosity, the more slowly the liquid flow. Hydrogen bonding and van der Waals forces are strong enough to cause high viscosity. Glass is an extremely viscous liquid. It is so viscous that many of its properties resemble solids. However, property of flow of the gases can be experienced by measuring the thickness of window panes of old building. These become thicker at bottom than at the top. Viscosity of liquid decreases at high temperature rises because at high temperature molecules have high kinetic energy and can overcome the intermolecular forces to slip past one another between the layers. Thank you.